So why don't you share your screen? We'll take a look at how you're doing it, and we'll just make sure you're doing it right. So this will be the first time a student has shared their screen. I kind of just want to see if it works, or if I have to change a setting. All right, here we go. Cool.
Can you see it?
Yeah, I can see your screen. All the stars in the background.
So this is what I have so far.
Okay, Kate Savage is here. Okay, so let's see. Well, it looks like I'm looking at number 9. Okay, so a couple things. Numbers 4 and 5, you should have, are those dotted lines? Or they should be dotted lines. Dory's here too. I can't tell if they are or not.
No.
It looks like you started with a dotted line and then went over it with a solid line.
Yeah, I think that's what I did because I confused myself.
Yes. Okay. So yeah, in the notes, remember, you can always remind yourself logically. Like we're looking at number 4 here. It says that y has to be less than 4. So what that means is y is not allowed to be equal to 4. If the y coordinate of the point is 4, then it's not a true statement, right? Does that make sense?
Yes.
Because 4 is not less than 4. So that's why we have to use a dotted line. The line itself is the boundary, and sometimes the boundary can be included as a solution. If we have that little line underneath it, it's a less than or equal to. But in this case, we have to use a dotted boundary line because the line itself does not contain solutions. Okay, the line is on y equals 4, and if y is 4, then we do not get a solution. We get a false statement. So that's the difference between a dotted and a solid line, and it basically comes down to when you use less than or greater than, the line is always dotted, and when we use less than or equal to or greater than or equal to, like in number 8 has a greater than or equal to sign, in that case we would use a solid line. So it looks like you got to fix that one too.
Okay.
Does that make sense? Because when you graph the line first, that's like our boundary. That's where that's what separates the solutions from the non-solutions. So sometimes, depending on the sign, sometimes the boundary line itself can contain solutions, and sometimes it can't. All right.
Okay.
Anna is here too, so we got a good group going. Let's see, and I saw one other mistake on number 9, and Morgan. All right. We got a grand old group. Okay, number 9. The one mistake I see here is you had a positive 2 and a negative x on the right side, but you got the signs flipped when you wrote it out. So that actually should be negative x plus 2 instead of negative 2 plus x.
Oh, okay.
So you're going to have a slope of -1, so the line should go downhill, and then you're going to have a y-intercept of, actually your y-intercept is still in the right place even though you had a -2 there. So I think you just maybe put the terms in the wrong order and got a little confused there, but yeah, your slope should be going downhill. All right, and Haley's here too, so we got a great group. Welcome to everybody who just joined. While we were waiting for everybody, Lena was just kind of showing me her work so far, and we were talking about what she was doing right and what she was doing wrong. So hopefully the rest of us can benefit from that. So yeah, like in number 6, what I was saying, Lena, is that your line should be dotted there because it says x has to be greater than 3. It cannot be equal to 3. So the boundary line where all the x values are 3, those points are not solutions. And if they're not solutions, we represent that with a dotted line. So the dotted line represents any point on that dotted line is not part of the solution set, only the shaded.
Okay.
Okay. So yeah, so I'm gonna go ahead and share my iPad and we'll get started. I figure, since we've already talked about it a little bit, we'll start with the application problem and then we can go back to any practice problems that you want to talk about. But I'm assuming there's some students here that want to talk about the application problem. Just make sure they're doing those right, and then leave, and that's totally fine. You can do that. So let me get back to
I
Zoom.
have two Mr. Schaabs.
Yes, one is my laptop and one is my iPad. So you'll be able to see me and talk to me, but at the same time, I can do stuff on my iPad. So I'll share my screen. It's good to see you all, or portions of you all. Morgan
Can you
is
see
like,
what I'm doing?
Morgan, are you in a tanning bed or what is going on there?
No, sorry. I'm turning my lights on.
No, that's fine. You don't have to change it. I like it.
Can you see what I'm doing?
Feeling a little blue today.
Yep.
Pretty cool that you have LED lights in your room.
Mr. Schaab, can you see what I'm doing?
Who said that?
Me, Haley. Can you see?
I can just see your forehead, Haley.
No, I mean like on the thing. Like, can you see that I'm saying go slower?
No.
No.
Oh, darn. There's a thing where I can
well.
Oh, I see that. Or go faster.
It's so cool. I can say go slower, and then you can go slower.
I can raise my
Yeah,
hand.
but I have to have this thing open.
Oh, okay.
I thought it would. I don't know why it's in full screen. I don't want to be in full screen. There we go. Okay, now I can see the side, and I can see if you hit go slower, go faster, yes, no, that kind of thing. All right, so that's the view I want. All right, but let's go ahead and jump into this. Okay, so first off, this is what we were talking about earlier. If you haven't seen this or wrote it down in your own notes, now I've been through all the packets from last week, but I haven't. No, wait. Yeah, from last week. Obviously, I haven't started grading this week's yet because not all of them are in. But you definitely need to know this. Okay, this will help you as long as your inequalities are in this form where it's solved for y. Just like we've always graphed a line. Then you can follow these shortcuts. It'll tell you exactly what you have to do if you need a dotted line or a solid line, and if you have to shade above the line or shade below the line. So this is kind of like our cheat sheet for how to use these 4 different signs. All right, and like we were explaining before, it makes perfect logical sense. You don't have to have the cheat sheet. Okay, you can use logic to figure it out. Like for example, what I said in this example here, since y has to be less than or equal to the boundary line. Remember, this expression represents the boundary line because this is what we're going to graph. So we graph the line first, plot all the points we can. We start at +4, and we use a slope of -1, and then run 3. So there's our slope of -1/3. And then because y can be equal to the line, we use a solid line. So any point on this line is a solution. It will make a true statement here. And then because y has to be less than the boundary line to be a solution, we shade all the y values that are less than where the line is. So that's basically, in a nutshell, how we use the sign that we're given to do the rest of the graphing. Okay. Hopefully you all feel great with graphing the line, using the slope and the y-intercept. But those are the 2 extra steps we need to do. We need to make sure the line is either dotted or solid, and we shade the right way to find, because remember, the shading represents all of the solutions to the inequality. So all the x and y values we could put in to give us a true statement. All right. So yes, this application problem is on my notes. I'm not going to talk about that, but we are going to do number 3. And remember, on the video, I did number 2. So if you're here today, you watched the video, and you read my notes, you should have the answers to all of them. Haley, do you have a question?
Morgan wants you to let her in. She accidentally got off, and you won't let her in.
Oh, I'm sorry. Okay, I didn't see that.
Oh, she's on now, I think.
I just let her in. I guess we'll let Morgan's iPhone in here.
Okay. Sorry, so I can see what you're doing and also look at mine.
That's okay. All right. So, and remember, if you do have any technical issues or you can't see what I'm doing, I'm going to post this video as soon as we're done here. So that it'll be there. You can go back and watch it again. Okay. So let's get our highlighters out because we want to find some information about this problem. Now, the nice thing about these applications is they already define the variables for you. So, we have fewer to do than last week, and they help us out with that, which is really nice. So let's pick some fun colors to use here. Let's go purple. Okay, so X is going to be purple. So X is the number of $5 tickets sold. All right, so let's see. Okay, so we'll use purple and green. All right, so X is the number of $5 tickets sold. Y is the number of $8 tickets sold. And then our constraint, let's do that in blue, is at least $1,200. All right, so like I said before, when we're setting up an inequality, the total or the constraint, you know, the condition that we need to meet, that's usually on one side by itself. All right, so we're going to start with 1,200 over here. So let's use blue. Okay, and what sign are we going to use if we want the money that we bring in from the dance to be at least 1,200? Anybody?
Less than or equal to.
Less than or equal to? So we want the money we bring in to be less than or equal to $1,200. Is that what at least means?
Yeah.
It's actually not.
No, greater than or equal to.
Yeah, that's what you think. When you see least, you want to think less than, but it's actually counterintuitive here. It's the opposite. At least means we could make $1,200. That'll be the bare minimum we could make, or we could make more. So it actually means we want the other side of this inequality to be greater than or equal to 1,200.
Oh,
right?
yeah.
So, all right, so if X is a number of $5 tickets sold, then all we have to do is multiply X by 5 to get the total money we're bringing in from those single tickets. So let's use purple. You can keep it. So it's going to be 5X. And then to that, we're going to add the money that we bring in from the couples tickets, which are $8. So $8 per couple. So $8 times how many of those tickets we sell, which is Y, gives us our inequality. Okay, so there we go. We got our inequality. It's in standard form. So what do we have to do if we're going to graph this?
Get Y by itself.
That is correct. All right, so let's do that. We'll do it in blue here. I'm going to have to write really, really small, but that's okay. All right, so 5X plus 8Y is greater than or equal to 1,200. Okay, we subtract 5X from both sides. These are not like terms, so we just throw them in there next to each other. So negative 5X plus 1,200. Okay, watch your signs really carefully here. A lot of students are going to be tempted to want to write 5X minus 1,200, but you can't do it that way. You're changing the signs of both numbers. So, all right, then we divide by 8, divide by 8, divide by 8. I know 120 divided by 8 is 15, so it should be 150. So we get Y is greater than or equal to, we do not have to flip the sign because we're dividing everything by a positive, so we don't have to worry about that. Negative 5/8 X plus 150. All right. Of course, at home, you're using your calculators to check and make sure you did that math right. All right. Okay, so we got our equation. Now let's graph it. All right, so we start by graphing the boundary line. We have our inequality, but when we graph the boundary line, we want to treat it like an equation. So, all right, so we start at 150. And let me move this out of the way because it's kind of getting in the way of my my scale here. Notice they didn't do all the numbers for you, so you might want to throw that in. Oops, make a little bit thinner than that. You might want to throw the rest of these numbers in here. They're going by 40s, but they just didn't do all the numbers, so we can fill in the rest here. Just go up by 40 every time. Okay, 40, 80, 120, 160, 200. 240, 280. Oops, what the heck did I do? Okay. So we're going to start at 150, which would be right about here. Thicker to make dots with. All right, and then now this is the tricky part. We're going to go down 5 and right 8. So how can we do this? Anybody got any suggestions?
Yes. Rise over run. Is that it?
Rise over run. But if we try and go down 5 and right 8, it's going to be really complicated.
Oh yeah.
So what's something else we could do? How can we change that slope so that we could go right 40 instead of going right 8? Let's think about that. Negative, keep forgetting. Okay. So I'll just do it over here. Negative 5/8. What's an equivalent fraction that has a 40 on the bottom?
the top would be 25.
Exactly, very good. Okay, so it'd be negative 25 over 40. So if we go down 25 and then we go right 40, that'd be a lot easier for us to graph. All right, so down 25 would be to 125, and then we go over 40. So right about here, just above 120. And that gives us our line. Okay, so now if we go down another 25, we'd be going down to 100, and then we go over to 80. All right, so 100 is right between 80 and 120. And you can see my line's not perfect, but it's good enough for what we're trying to do here. So if we go down another 25, it'll be 75 and then 120. So 75 is just below the 80 line. And then down another would be 50, so just above the 40 line. And then 25, so maybe right there. All right, and then 0 and 240. So it's not, not really easy to find those points on the graph, but you can do it. And the problem is we really just can't go down 5 spaces because we don't have 5 to work with. So we have to kind of make adjustments there. Okay, but we got our points. So now somebody tell me, are we going to use a solid line or a dotted line?
Solid.
Yeah, it's going to be solid because its y is greater than or equal to. So let's do that. Okay, we don't really need to put points on it or arrows on it. And you can see my points aren't perfect, but that's okay. I'm not looking for perfection here. So I just want to see that maybe you got the first point in the right place, and definitely the last point in the right place. All right, at 0, 240, or 240, 0, I should say. Okay, and then are we going to shade above or below the line? Look at the sign we got. Yeah, we are going to shade above. So we shade everything, and then all these points here would be solutions. It means that the school would make enough money in the dance, okay, to cover the cost of expenses. If they sell any combination of tickets in here, they'll be good. So like this point right here, that point is they sell 160 single tickets and 200 couples tickets. They'll make plenty of money. They're going to make way more. Remember, this boundary line here, this is where if they make exactly $1,200. So any point up here, the further away it gets from the line, the more money they're making. All right, so this would definitely be a solution. We could plug that in for X and Y, and we would definitely get an answer that's bigger than 1,200. So that's just kind of how that works. Okay, so number 7, which of the following is a solution to the inequality? Well, that's just like I was doing in the other problems. We'll use green here. And we're just going to plot these points on the coordinate plane and see if they fall in the shaded region or if they don't. If they fall in the shaded region, that means they're a solution. If they fall in the unshaded region, it means those numbers for X and Y will not yield them enough money to cover expenses. So 160 and 40 would be right here, and you can see that is close, but it's outside the shaded area, even though my shading is not perfect. This is what, 40, 160. No, 160 and 40 is what this one is. Okay, how about 40, 160? Well, yes, that one is actually in the shaded region. So that's going to be our answer. And just to make sure, we want to make sure 80, 80 is not in there either because there only has to be one. So yes, this is 80, 80. Only one of those points is in the shaded region. So we're going to pick 40 and 160. So we go down here, cross that out. This is number 7. Okay, just to remind ourselves where that answer came from in case something's wrong. We can go back and fix it quickly. Okay, So somebody help me out with this one. Number 8, how many $8 tickets must be sold if no $5 tickets are sold? So what are they really asking you? Let's think critically about it. What does no $5 tickets really mean in this problem?
No, just one person tickets. Like they.
And what variable represents the one person?
X.
Exactly. So they're saying X is 0. What is Y when X is 0? All right. So if they sold no single tickets, how many couple tickets do they have to sell to make $1,200? So if X is 0, then that means we start. Let me get my laser pointer out. We start here and we don't go left or right. So we just have to go up. So what's the bare minimum of couples tickets that we can sell? To be on the line or in the shaded region. What do you think?
Like 140 or 150.
What is it? Yeah, it was 150, right? That's our y-intercept. Okay, so it should make it. Yeah, right. It should make sense if we take the inequality, -5/8, and we put a 0 in for x. Then this whole term is just going to be 0, and that drops out. Y is greater than or equal to 150. So 150 is the bare minimum they can sell. They can sell 160. They can sell 200. They can sell 400. Those would all meet their quota. But if they sell 149 tickets, they're going to be short of covering their expenses, those $1,200. So the answer here is 150. So we find that. That's right here. Letter B, we're going to cross that out, put a number 8 there. All right. So now this is a great question here. If X equals 80 tickets, what are all the possible values of Y? So let's go to our graph. If X is 80, then we're looking at this vertical line right here, okay? So what's the minimum that Y can be? What do you think? Anybody remember what that point was?
100?
Yeah, it is 100. Because remember, we started at 150 and we went down 25 and over 40. Down 25 over 40. So going down 25 twice from 150, that would be down to 100. So, and of course, there is a way you can figure that out by plugging in 80 for X. So if you plug in 80 for X and you work that out, we'll get Y is greater than or equal to 100. And then, but we're not quite done yet. Does Y have to be exactly 100 or can it be other numbers?
It can be other numbers because it can be greater.
It can be greater. So it can be 100 or literally any number greater. There's no roof. There's no ceiling to how high that number can go, right? They could sell, I mean, there certainly is. In a real world situation like this, a student or a school only has so many couples that can come to a dance. But theoretically, for what we need to do here, we just have to know that Y is greater than or equal to 100. So this is the one that we want right here. Y is greater than or equal to 100. If Y is equal to 100, they make exactly $1,200. If Y is greater than 100, they'll make more than $1,200. So this is the expression that we want to use. So we're going to cross out the R, put a number 9 here. Okay, so, and then the answer would be Y is greater than or equal to 100. And we know that just from looking at the graph. This is where, if X is 80, this is where the solutions for Y start, and then you can tell from the shading that they go up. And of course, they're not going to stop at 280. They could sell 300, they could sell 400, and they would definitely make their money. So that's how you do them. As always, the difficult part is usually getting the inequality written down. So hopefully you're getting a good feel for how to do that. Okay, so any questions on this or any of the other applications? Okay, well, like I said, if that's all you wanted to talk about, then you don't have to stick around. But if you have some other questions, I'm here till noon.
Are we gonna have like a test or anything at the end of this?
Yes. So, and I said I put something in the weekly agenda about that this week. So So basically, we've covered systems of equations. So solving by graphing, solving by substitution, solving by elimination, special systems. We're going to do graphing linear inequalities, and next week we're going to do graphing systems of linear inequalities. So basically, you're going to be doing this process, but you're going to be doing two inequalities at the same time and finding the solution region that way. So it kind of piggybacks off of this. And then week 5 is going to be review for the Unit 5 test. You're going to have an entire week to do a review packet. At the end of that week, I will post the answer key to the review packet, but of course I want everybody to do it on their own and turn in their work for their own. And then the very last week, you're just going to have a test that you take on Friday. So you'll have the entire week to check over your answers from the packet. I'll definitely put more resources up, but they will be optional, just like maybe a puzzle worksheet if you want to get some extra practice or something like that. But yeah, the very last week, you're just going to have a test, and then that's going to be it. You're going to have a test over Unit 6. So that's coming up quickly, and then there's going to be nothing cumulative, no final, no cumulative packet over the whole semester. I'm trying to keep it simple, and I'm trying to, systems are really important for us to know when you go into unit 2, when you go into Algebra 2. So I'm glad we got this entire unit covered. Anything beyond that was just icing on the cake anyway. So so yeah, we're gonna keep it simple, and that's what's coming up the rest of the year. You'll have one more packet like this in week 4, then you'll have a review packet week 5, and then you'll take the test week 6. Good?
Yeah, will the test be timed?
No. I'll probably give you the entire day on Friday. You'll get it in the morning, and you'll just have to turn it in your own handwriting, obviously, by 3 p.m. And it will be shorter than a normal test. It's definitely not going to be 2 hours of work. I'll probably just give you a couple problems from each and a couple applications, and that'll be it. So my goal is the average time will be about an hour or less to take this test. So some of you it will take longer, some of you will not take as long. You know how that goes, but yeah, it's gonna be short and sweet, and I'm just testing you on can you do the basics from this unit, because this is the last really important unit that we had to get through. All right. So any questions on the practice problems? Why is my iPad not moving? Oh, it's just moving really slow.
Can we do number 12?
Number 12, sure. Okay, yeah, these are a little bit more complicated because we have to get y by itself first. So let's do that. Get out. Let's keep it red. Okay. So the first thing we're going to do is add 2x. That's a negative 2x. So remember, we want to turn it into a 0 to get it to the other side. Sorry, my iPad's taking a really long time. I wrote it down like 10 seconds ago. There it is. I don't know why it's lagging so much. That's the first time it's done that. But anyway, okay. So I'll bring it up here. 3y is greater than. I always slide that x term in front of the constant, just because that's what we're used to seeing. So they're both positive, so we add 2x plus 6. And then we have to divide everything by 3. So divide by 3, divide by 3, divide by 3. We're dividing by positive again, so we don't have to flip the inequality sign, but that is something that you have to remember and think about. So we get y is greater than 2/3 x plus 2. All right, 6 divided by 3. Okay. So now we're ready to graph the boundary line, and then we can figure out if it's dotted or solid and if we shade above or below. All right. So our y-intercept is positive 2, and then we go down to right 3. I'm sorry, not down to, up to right 3. It's a positive slope, so we want to be going uphill. Those are the only 3 points we can fit, so that's all we have to really do. Okay. So somebody tell me, are we going to be using a dotted line or a solid line here?
Dotted.
Dotted, yes, because of this guy right here, a greater than sign. If we go up to the cheat sheet, a greater than sign, dotted and shade above. So yeah, it's really behind. Okay. So dotted and shade above. So that's what we're gonna do. So not always easy to draw a dotted line on an iPad, but Apple pencils really help. Okay, put some arrows on that, and we shade above because y has to be greater. The y coordinate to be a solution has to be greater than the boundary line. So that's where our greater than, that's where our numbers are greater, up above this line. Okay, so we shade, fill that in. Perfect. All right. That's what it looks like. And remember what this represents. Any point that's in this region is going to give you a true statement when you plug it in for x and y. So like if I take even something really close to the boundary line, like the point -3, 1, all right, if I put -2 times -3, if I put a -3 in for x and a 1 in for y, I should get a true statement. And let's see what we get here. So we get 6 plus 3 is greater than 6, and of course that is true. 9 is greater than 6. I can't write, but so yeah. So that's what that means. That's why we're graphing this. I just want to make sure everybody understands why. And that's probably the hardest one you have to do in the practice problems because you have to get it in slope-intercept form. Okay, 10 is like that as well. All right, so how are we feeling?
I'm good. Thank you.
Good, great. Okay,
Thanks.
no problem.
Thank you.
You're welcome. See you later. Okay, anybody, if you want to stick around and ask a question, or if you want to share your screen and let me take a look at your work, I'd be happy to, or you can head out and enjoy the rest of your day.
Thank you.
You are welcome. See you, Dory.
Mr. Schaab, I have a
Yeah.
question.
Sure, what's up?
Okay, so for number 10, I'm kind of confused still. So,
Okay. So you tell me what you would do
check it
first.
out. So
Yeah, why don't you, we'll talk through it together.
Okay, so I would do minus x first
Right.
on both
minus
sides.
X. Yep. Okay, and now what do you have?
And then y is greater than or equal to negative x minus 3.
Perfect. Okay, now do you have to divide anything?
No.
No, right? Now it's good to go. It is in slope-intercept form. Okay. So what do you do first?
You would go down to -3.
Yes, we would, and we put a point on the y-axis at -3.
And then would we go down 1 and over 1 to the left?
Down. Well, you go down 1, but then you have to go right. Remember, with a negative slope, this is a -1 over 1. Let me write that differently. It's a -1 over 1x. So one of the numbers is negative and one is positive. So you can't move, if you move negative in both directions, then a negative divided by a negative is actually a positive. So you'll end up getting a positive slope. So you have to go down, but then you have to move right to get that downhill slope that we want. Because
Okay.
the rise is -1, but the run is +1. And that's a little bit confusing when you're dealing with a negative slope. Students think like both numbers should be negative, but it's a fraction. They're really not. So,
Okay, that makes sense.
yeah, so this is where our boundary line would be going. Okay, and then you just have to tack on the 2 new rules that we learned about, like do we shade above or below, and do we use a dotted or solid line? That all has to do with this sign right here. So you tell me, how would you finish this off?
It would be a solid line,
Good.
and then you would shave above.
Yep, you got it.
Okay.
The most fun part. Okay, so yeah, that's what it's going to look like.
Okay.
All
That
right,
makes
so it
sense.
sounds like you got a good handle on it. Just take your time and talk yourself through it. That might help.
Okay, thank you.
You're welcome, Lena. See you later.
Bye.
Bye. Bye.